In this lecture, we're going to talk about step growth or condensation polymers. Here's an example of a step growth polymer. Step growth polymers typically have carbonyl containing functional groups. And you can see that we have a carboxylic acid on this end that reacts with one end of an ethylene glycol. And we also have a carboxylic acid on the other end that reacts with another ethylene glycol. The ethylene glycol then can also react with another equivalent of the carboxylic acid, and so on. So remember that what happens when we have this type of reaction is this is just an esterification. Under acidic conditions, the carboxylic acid gets protonated, and then the alcohol can attack. This can happen on both sides. You can imagine that the carboxylic acid on the other side can also get protonated and another ethylene glycol can attack. So this would give you something like this. And then remember there's a proton transfer where we take off this proton and we protonate one of the alcohols because one of those is going to come off. I'm going to skip those steps and just go to what we would have a couple of steps later. So we have something like this, and then we kick off the water. And then you would deprotonate, and then the other end of the alcohol would attack another protonated carboxylic acid. And I also didn't draw out the R group over here, but you'd have another carboxylic acid on the other end that is also reacting with another equivalent of ethylene glycol. Eventually, you end up with a long polymer chain that looks like this, or can also be represented like this. Here are some more examples of step growth or condensation polymers. In this case, we have an acid chloride reacting with an amine. You don't even need to add anything here to get the reaction going and get this nice polymer of nylon 66. Remember that we have a pretty reactive acid chloride, so the amine is just going to attack directly. Right, the electrons come up. We have a proton transfer from another amine. And then we can come in here and kick out the chlorine. Right, so all this is an addition-elimination reaction. You can see here that then on the other side of the R group, there's another acid chloride that can react with another equivalent of hexane diamine. And on the other end of the R group on the right here, you have another equivalent of amine that can react with another acid chloride and form our polymer chain. Here's another example with diphenyl carbonate and bisphenol A. Under high heat, the alcohol can attack the carbonyl group, and this is just a trans-esterification reaction. Urethane step growth polymers are pretty neat because they use this isocyanate functional group that we haven't seen before. So we have an alcohol attack the isocyanate. There's a little bit of a non-nucleophilic amine present, and then we can form a urethane. If you have an isocyanate on two sides of the molecule and you have a diol, then you can get a polymer chain to form. The alcohol is going to attack our carbon over here and push electrons up to the oxygen. Okay, we're going to have a couple of proton transfers. You can see here that our non-nucleophilic amine can come over here and pick up a proton. And then we have resonance to put the negative charge on the nitrogen. And then a proton transfer to protonate that negative charge. And that would give us the urethane shown here. A specific example is shown here, where you have an isocyanate on both sides of this molecule. Each of those can react with one end of an ethylene glycol, and eventually we get a nice long polyurethane chain. Here's a picture showing the growth of the polymer chain in step growth polymerization. This is showing an example with adipic acid and hexane 1,6-diamine. Adipic acid has a carboxylic acid on both ends and looks like that. And hexane 1,6-diamine looks like this. You can see that an adipic acid then can react with any hexane diamine and start to react. Each of these little pieces then can continue to react with other pieces. And as they're doing that and forming longer chains, new chains can start to react. So either end of these molecules continue to react. It's very different from the step growth polymers where we had to have that initiator get the chain started. Here's another example of a step growth or condensation polymer. You can see here that the phenol can react with formaldehyde, and the formaldehyde carbons are all shown here in blue. When this reaction occurs, you can see that we're losing water. And because of the way this works, you have a phenol, which is an ortho-para director, then you can have the reaction occur at any ortho and para position. So this particular polymer is called a network polymer because it doesn't have any defined linearity. That means that it's not forming a long chain, it's just kind of growing in all different directions.